Welcome everyone to the first Extension 1 lecture for maths. I'm Arpon. I'll be your lecturer for today. So, bit of housekeeping. So if you have any questions, please drop them in the chat. I'll address them as soon as possible. All of our notes will be uploaded to the Zoom chat at the conclusion of the masterclass. Now, because it's Permutations Comms, a pretty hard module, this masterclass might go until like 9 p.m. So I will upload them at 8:30 p.m. and you can choose to stay or leave after 8:30. Up to you, right? If you can't attend the full session or you know someone who missed out, a full recording will be uploaded to YouTube afterwards. I'll be here at the end to answer any questions. Also, like, if you guys can, turn your cameras on because right now all I see is a bunch of black screens. But again, up to you. So about myself, I'm a tutor at Summit. I'm focusing on chemistry, maths, extension 1 and 2. I graduated senior grammar school with an ATAR of 9.95. I have 3 years of teaching experience. In regards to maths, my stats are there. I came first in senior grammar for E1 as well as E2. And right now I'm doing a Bachelor of Science and Doctor of Medicine at the University of Sydney. So about Summit, it's tailored online group classes with about 4 to 6 students to make sure like you guys get personalized attention. We're offering the following subjects on the screen there, and all of our tutors have achieved either a perfect ATAR or a state rank, and you'll have access to all of these resources as you should. So for Perms and Comms in particular, like it's the module I hated the most in year 11, but I got really, really good at it in year 12. And it's because, you might have heard on Reels like, yo, have a mistakes book. It's gonna be so good for you. This is one of the topics where you do need a mistakes book. There's different strategies for different questions. And so what I've done in today's lecture is like I've compiled every single question you might have to know for Perms and Comms. So if you're able to do all of my questions from these lectures by yourself at home, you should be quite comfortably like set for year 11 and year 12 exams, right? So it's very important to have a mistakes book for this topic. And you might want to like organize all of your questions based on like different strategies. You'll see the gap strategy, the bubble strategy, the stars and bar strategy, all of which I'll cover today. So yeah, let's get straight into it. That's it for these slides. And it's time to do perms and comms, right? Perms and comms, those are all the topics for today. I'm gonna start with the counting principle, move on to the pigeonhole principle, and then I'm gonna give you like a brief interlude on understanding how perms and comms formulas are derived. And then from then on, it'll just be practice questions for the entirety of the session, right? The counting principle. So the first one is the multiplication rule, and it's pretty like intuitive, right? If I have 3 ways to go from A to B, and then I have 4 more ways to go from B to C, then I have 3 times 4 ways to go from A to C, right? 3 times 4 is 12. That's all it is. Each option, each choice is independent, it's all sequential. And we can do this question like right now. So a computer password must have 8 characters. The first 3 must be letters, uppercase or lowercase. The next 2 must be digits. And the last 3 must be special symbols chosen from those 6. How many different passwords are possible if repetition is allowed? So first of all, I don't know why, but I always have to draw like these dashes for A. So 1, 2, 3, 4, 5, 6, 7, 8. The first 3 must be letters, uppercase or lowercase. I have 26, I have 26 uppercase and 26 lowercase, 52 times 52 times 52, my first 3. The next 2 must be digits. I have, okay, 0 to 9, that's 10 digits. 10 times 10. And the last 3 must be special symbols, so I have 6 options. I can repeat, so 6 times 6 times 6. So my answer is just 52 cubed times 10 squared times 6 cubed. Not too hard. I won't do that in a calculator. It's too long, waste of time. The addition rule is like when you have multiple ways to complete the same task. Like for example, if I have like 3 different bus routes to go from like this is really bad. 1, 2, 3. 3 ways to go from A to B on a bus, and like 4 ways to go from A to B on a train. Then in total, I have 7 ways to go from A to B, right? So these are multiple mutually exclusive events. So let's just move on to the question. Yeah, Also, I'm going to note here, be careful of double counting, and this will be apparent in this question. A student can reach school by bus, train, or car. There are four bus routes, three train routes, and two car routes. However, due to maintenance, two of the bus routes and one train route are temporarily closed. In addition, one bus route and one car route go through the same street. How many ways can the student reach school? So let's do some addition, right? Like 4 ways to get to school. We have 4 plus 3 plus 2 from here. But then some are like cooked, right? So we -2, -1, right? Two of the bus routes and one train route closed. And then in addition, one bus route and one car route go through the same street. I'm double counting, right? In that case, I would -1 again. So 4 plus 3, 7 plus 2, 9, -2, -1, gives me 5. And my answer is 5. Hopefully that's true. And we'll now move on to the pigeonhole principle. So the pigeonhole principle. And the entire intuition is that if you have more items than there are containers, then at least one of these containers will have at least like 2 items, right? If I have, let's say, 4 boxes, right? I have 4 boxes and I have 5 Lego bricks. If I spread out these Lego bricks evenly, right? I put one in the first one in the second one in the third one, and one in the fourth one. No matter where I put the fifth Lego brick, at least one of these boxes will have two, right? It'll have two. So that's literally what's going on here. If you put n items into k containers, then at least one container has at least the ceiling function of n divided by k items, right? So what's the ceiling function? It's like the ceiling function of 3.1 is 4. So it basically rounds up to the nearest whole number. If I have 5 Lego bricks into 4 containers, that gives me 1.25, right? But I can't have 1.25 objects in a container. I can have one or two. So I apply the ceiling function, and that gives me 2, right? Or I might have, let's say, 7 Lego bricks and um 4, no, let's say 3. 7 Lego bricks into 3 containers, right? Let's spread them out. 1, 2, sorry, 1, 1, 1, 2, 2, 2. The seventh one has to go in any of these boxes, and no matter what, I'll have at least one box with 3 Lego bricks, right? So the I'll have the ceiling function of 7 divided by 3. I can't do that in my head, but that's the ceiling function of 2.33, which is 3, right? So I have at least one box with 3. And that's what's going on over there. Um, Here's the alternative form, but before I get onto that, let's do an example, right? So my question here is, at least one of 4 boxes must have at least 3 balls. What's the smallest number of balls you need? So if I have 4 boxes and they must have at least 3 balls, if you want to spread them out as much as possible, let's put 2 in each. 1, 2, 3, 4, 5, 6, 7, 8, right? And no matter where we put in the ninth ball, at least one of these boxes will have 3 balls, right? So what I've done here is I've done 4 times 2, 4 pigeonholes times 2 balls. I'm adding 1 to force there to be like at least one box with 3 balls. And that's what this formula comes about. So n equals k times r minus 1 plus 1. And this formula is in order to answer a question where you have to guarantee that at least one container has R or more items. So if I have K pigeonholes, right? K pigeonholes, and by pigeonholes, I'm referring to like these boxes, for example, right? What I'm gonna do is put in R minus 1, right? For example, here I had 4 pigeonholes and I put in 3 - 1 balls into each, right? So R minus 1. And what that guarantees is that no matter where I put this last ball, the last +1, I will always have at least one container with our balls. So question 1, given at least one of 5 pigeonholes has at least 4 pigeons, find the minimum number of pigeons needed. So in the chat, give me the answer. Shouldn't take too long. Yep, Jackie, that's correct. 16, right? So the way you do this question, right? Well, method one is just let's just use our brains for a bit. We have five pigeonholes, one, two, three, four, five, right? It has at least four, so we're gonna force there to be three in each. One, two, three, one, two, three, one, two, three, one, two, three, one, two, three. So we have five pigeonholes, three each. There's 15. And then we want there to be at least four pigeons. So let's add a plus one somewhere. Because no matter where I put this green pigeon in, I'm gonna have at least one box with four pigeons. 15 plus one gives me 16. Or just use a formula. So n equals to 5 times 4 minus 1 plus 1, giving me 16. Okay. The next question is a multiple choice quiz asks students four questions. Each question has three possible answers, A, B, or C, and students must attempt each question. How many students must do the quiz to ensure that at least two sets of answers are identical? I'll give you guys about a minute to think about it, and then I'm gonna go through it to show you what the approach would be. And if you get the answer before that, just like put in the chat and then I can verify for you. Cool. Good work, Aiden. So Aiden told me that the answer is 82. So how did he get that answer? First of all, in any question, I don't know why, but I do like to draw a diagram. So we have a multiple choice quiz. Let's like draw it out. One, two, three, four. We have four questions, right? We have A, B, C, A, B, C, A, B, C, and A, B, C. And here's where you'll see the multiplication rule being useful, right? Because if each question has three possible answer options, then in total, I'm going to have 3 times 3 times 3 times 3 possible answer sets, which gives me 81, right? I have 81 possible answer sets. This means that if I have 82 students, right, I'm going to have at least um two students who have the identical answer sets, right? And the entire intuition is that if I imagine each possible answer set being a pigeonhole, like one, two, all the way to the 81st, right? In the most like, obscure case, I could have like one student in each of these pigeonholes, right? So that's 81 students. And this means that no matter where I put my 82nd student, he'll always be sharing a pigeonhole with someone else, and therefore he'll have the same answer set. So my answer here is just 81 plus 1, giving me 82, right? Just guarantee that he's always going to have the same answer solution. Now, question 3 is going to be probably as hard as pigeonhole principle questions can get. So the way I've structured this section is that number one is super easy. Number two is like the average question. And number three is like the really, really hard ones that you could get, right? So here, a regular octahedron has six vertices. Each vertex is connected to another vertex by a rod that is colored yellow or blue. Explain why there will be at least one triangle whose rods have all the same color. Now for this one, I'll just go through it because I remember when I was in year 11, this one stumped me, but now I kind of get it. So how do you approach this? So it's an octahedron, right? It's like this shape, two square pyramids overlapping with each other, okay? And it has six vertices. Each vertex is connected to another vertex by a rod that's yellow or blue. So if I consider vertex one, right, let's be V1, one over here. I can either connect this vertex to um five other vertices. One, two, three, four, five, right? To five other vertices. So if I have five vertices, then that means that with from point one, I can form about five rods. One, two, three, four, five, right? Given that I have five rods and two possible colors, by the pigeonhole principle, right, using for the first time, at least five onto ceiling function rods will have the same color, right? 5 divided by 2 is 2.5. Ceiling function gives me 3. Okay, 3 rods. At least 3 rods will have the same color. So in this case, let's assume I have 3 blue rods being the same color, right? 3 blue rods being the same color. Now, my next question is, I'm trying to figure out how I can get a triangle whose rods all have the same color. So at this point of the question, I'm not concerned with the rods like in between 2, 3, 4, and 5. Oh no, there should be 2, 3, 4, 5, and 6. Okay. So if I consider the 3 blue rods over here, 3 blue rods, between these 3 blue rods, I can form 1, 2, and 3 other rods, right? I can form 3 other rods. And with these 3 other rods, by pigeonhole principle, at least, so at least 3 divided by 2 ceiling function rods will be the same color, right? So, I might have, okay, so 3 divided by 2 is 1.5. Ceiling function will give me 2 rods. At least 2 rods will be the same color. So, for example, I might have 2 blue rods. So, if I have 2 blue rods, then this would be a monochromatic triangle, right? A triangle whose rods are the same color, or the triangle formed by 2, 4, 1 will also be a monochromatic triangle, right? If I have 3 blue rods, easy, right? I have a triangle that has the same color. Now, the issue is I might have 2 blue rods, right? But at the same time, I can also have 2 yellow rods, right? But even if I have 2 yellow rods, um, the last one is a blue rod, right? This is a triangle whose rods are all the same color. But then what if I have 3 yellow rods? What if all the rods here are yellow, right? Because that's still possible. Because in part two, I'm saying here, at least 2 rods will be the same color, right? And it's the same color. It's not blue or yellow. It's either blue or yellow. So there is a chance where I can have all 3 being yellow. But that's not an issue because if all 3 of these rods are yellow, then that in and of itself is a triangle whose rods are all the same color, right? So the way I would frame this question is, first of all, by pigeonhole principle, at least 3 rods will have the same color, right? And then for my second step, I would be like, I'll put some more detail here. Um, if you consider the vertices, who share the vertices um that share the same color as per part one, right? Three rods can be formed in between these vertices. Okay. Um, and by pigeonhole principle, by the way, don't say PHP in your exam, say pigeonhole principle, you might get marked down. Um, at least two of these rods are of the same color. Now you have two cases. The first case is if at least one of the rods shares the same color as part one, right? Maybe like shares the same color as these blue rods, right? We might have a blue rod over here. Then a monochromatic triangle is formed. If all three rods, or like if all of the rods are of a different color to one, then those rods themselves form a monochromatic triangle. So no matter what I do, I'm always going to have a triangle whose rods all have the same color, right? So two things to note here. Number one, this is probably the hardest question you'll get for pigeonhole principle. Number two, be like ready to write an essay. Like you have to have step-by-step logical reasoning. Um, if you have multiple cases, explain each case. You can't cheat your way out of an essay for these kinds of questions. You have to do writing. Actually, two more things to note as well. You can just draw a diagram to help you out. Like I would draw, six vertices and like a bunch of lines in between because it would help me out. And number four, if you have any question that involves the words at least, you have to use pigeonhole principle. Any other method is probably way harder than using pigeonhole principle. All right. So that's it for section two. And now we're going to move on to perms and coms in general, right? So perms and coms, the most common question might be like, look, you have three people in a line. How many ways can they stand in line, right? How many ways can they stand in line? And this is pretty easy. So if you have like a door, right? Maybe they're trying to like buy a pastry from a bakery. In the first spot, I can have three people standing here. And then because that third person is standing over here, there's only two people left. So I have two for the next one and one for the remaining one. That's 3 times 2 times 1, giving me 6. What if I have more people than there are spots? What if I have 4 people standing in line? What do I do about that? Well, still the same logic, right? I can have 4 people standing here. So okay, standing in a line that has 3 spots. It's a bit weird, but it has 3 spots, right? I can have 4 people in first. I can have 3 in second. I can have 2 at last, right? So my answer is just 4 times 3 times 2. If I have 100 people in 100 people doing city to surf, right? How many ways could there be like a podium? Well, yeah, podium finish, right? So for podium finish, we have first, second, third, right? Gold, silver, bronze. I can have 100 people over here, or I could have 99 for the second place and 98 for third place, right? So my answer is 100 times 99 times 98. So how do I generalize this? The formula for these sorts of ordered arrangement, right? I'm saying ordered because here order matters. If you're first, that's different to being second, which is different to being third. The formula for an ordered arrangement is NPR is equal to n factorial over n minus r factorial. So what n is how many like total things are we going to arrange? And then R is referring to how many spots do we have? In terms of derivation of this formula, if you have n people wanting to fit into R spots for like Drake tickets on Ticket Tech, right? So we have 1, 2, 3, right, all the way to here. I can have n people in the first spot, n minus 1, then n minus 2, all the way to n minus r plus 2, then n minus r plus 1, right? And this is equal to, so this is just n times n minus 1 times n minus 2 times all the way to n minus r plus 1. What I can do, a bit of a mathematical trick, is times, n minus r, then times n minus r minus 1, all the way to times 2 times 1, right? Times 2 times 1. And on the bottom, I can write n minus r times n minus r minus 1 times all the way to times 2 times 1, which is just n factorial over n minus r factorial. And for those who aren't too sure what a factorial is, it's just like a simplified way of saying um, the following. So if I have 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, that's a bit tedious. Let's say that's 8 factorial. If I have 6 times 5 times 4 times 3 times 2 times 1, that's 6 factorial. So if I have n factorial, that's just n minus 1 times n minus 2 all the way to times 3 times 2 times 1, right? So do with whole numbers. You can't have 3.1 factorial, makes no sense. Whole numbers, right? So that's ordered arrangements. But then things get a bit annoying if you have like combinations, right? Let's say I have um 6 people, right? I have 6 people. I want to form a committee of 3. Okay. So I will just like draw up my dashes, 1, 2, 3, right? Based on my perms and coms logic, I'll be like, okay, first spot 6, second spot 5, third spot 4, right? 6 times 5 times 4 gives me what? 120. And then the answer is wrong. And the reason for this is that it's this gives me an ordered arrangement, whereas here it's unordered. What does that mean? Let's say we have 3 people, A, B, C. If I have A here, B here, and C here, right? Our first solution treats ABC as being different from ACB, from CBA, CAB, and like BAC, BCA. These are all treated as different, even though functionally it's the same thing. I've picked A, I've picked B, I've picked C. That's one case. Why do I have 6? Right? So the right answer is just 120 divided by 6, giving me 20, right? Or it is 5 factorial, sorry, 120 over 6. Wait, 120 over, yeah, 6. Or it's just, sorry, 120 over 3 factorial, giving me 20. So in essence, right, the way you can connect this back to permutations is that it would just be NPR divided by R factorial, right? I'm going to do an ordered arrangement of these R things and then divided by how many ways there are to arrange the R things themselves, right? So here, I have a ordered selection of 3 things from a total of 6, and then I divide it by 3 factorial because there are only three factorial ways to arrange 3 things, right? I can, move it around like that, if that makes sense. Okay, in the chat. Okay, never mind. The next thing I want to talk to you guys about is the bubble strategy. Oh, actually, for purpose of comms, the full formula here is NCR. So combinations is equal to NPR over R factorial, which is just N factorial over N minus R factorial times R factorial. So R is things we choose, and N is like the total. Like from a total, we're picking R things. The next strategy to talk about is the bubble strategy, right? So bubble strategy. For example, how many ways are there to arrange A, B, C, D such that B, C is together, right? B and C are together. So what I'm gonna do now is because B and C have to be together, I'm gonna put B and C into a bubble, right? I have A, B, C as my bubble, and then D. Okay. So even though I have four letters, I'm just gonna arrange three bubbles where B and C are together. So my answer is 3 factorial, giving me an answer of 6. But the answer is wrong. Can someone in chat tell me why my answer of 6 is wrong? Yeah, so Jackie said, and Nikhil, right? B and C have to be switched. Like they can be arranged, right? So I could have C being in front of B. I could have B being in front of C, right? I can have BC or CB. So my correct answer is going to be 6 times 2 factorial, which is 12, right? Because I can arrange BC in two ways, right? Um, that's generally what the bubble strategy is. I'll go way more in depth within my lecture PDF. And the last one is the gap strategy. Um, you know what? I'll cover that in my PDF. There's a better like example there. So let's start with some questions, right? Permutations. Um, how many five-letter words can be made from the letters in the word question? So question has 1, 2, 3, 4, 5, 6, 7, 8 letters. And I'm gonna put five, no, I'm gonna put 8 letters into 5 spots, right? And the order matters. So my answer is just 8P5, which is just 6,720. Or if you're not too like comfortable with the notation of AP5, you have 1, 2, 3, 4, 5. I have 8 options here: 7, 6, 5, 4. So it'll be 8 times 7 times 6 times 5 times 4. And I'll give you the same answer, right? Skip this. Oh, how do we arrange stuff if we have repetition? So the example here given is that what if you have triple A and then B? So based on what we've learned so far, you might be like, okay, there's 4 objects, right? So to arrange 4, it will be 4 times 3 times 2 times 1, giving me 24, right? But the issue is that if I number like all 3 A's as being A1, A2, and A3, and then I consider all the arrangements, A1, A2, A3, A2, A1, A3, A3, A1, A2, A1, A3, all of that, right? It still looks like A, B. These all are the same like arrangements. So in that case, my answer can't be 24. I have to divide by a certain number to get rid of all these like I guess triple counts, right? So essentially, because I have A1, A2, and A3, if I imagine just arranging A1, A2, A3, I have 3 factorial ways to arrange 3 objects, right? And these are 3 identical objects. So what I'm going to do is do 24, my total, divided by 3 factorial, giving me 4 arrangements that work. Yeah, 24 divided by, yeah, it's 4. So in this example here with Mississippi, right? Mississippi has 11 letters. So in total, to arrange 11 objects, it would be 11 factorial. I'm going to divide this by all the repeats. So I have four S's, I have two P's, and I have one, two, three, four. I have four I's. So it'll be 11 factorial divided by 4 factorial times 2 factorial times 4 factorial, which would give me a pretty big number. Let me see what it is. 4 factorial times 4 factorial times 2 factorial. 34,650. And that's my answer. Okay. Now, the reason why I want to cover groups was because this question deals with repeats, but it also needs groups. So essentially, in these permanent comments questions, you can have like multiple strategies being combined together. So let's see how to deal with this one. And this is a pretty hard question. It was in my year 12 trials, I think. Not too sure. But and it stumped most of the grade because we all forgot to like um account for one important factor. So let's deal with this. How many arrangements of the word double A, triple B, C, triple D contains the subword BDA? Okay, the subword BDA. Um, what I'm gonna do is consider BDA as a bubble. So I'll have A, then A. No, I'll have A and BDA as a different bubble. I'm gonna have two B's remaining, a C, and two D's, right? So in total, I have one, two, three, four, five, six, seven bubbles, right? I have seven factorial arrangements in total, but then again, I have two repeats, right? I have double B's and double D's. So it would be 2 factorial times 2 factorial in my denominator. 7 factorial divided by 2 times 2 gives me 1260. And this is the answer my entire grade put in, right? But it's wrong. Does anyone know why this answer is wrong? Like you do have to do this working out to get to the answer. But if you just put this in, it would be incorrect. Why? BDA can be rearranged. Um, I think in this question, like BDA has to be in that order of B, D, and A. Like you don't times by 3 factorial to arrange BDA. It just has to be that one case. Jackie says, is it because there are multiple B and A and D? Correct, right? There's multiple B, A's, and D's. So why did I pick BD? Like I did BDA, right, with, this B, this D, and this A, but why could I not just use this B, this A, and this D to form a different BDA, right? So there are multiple ways to form the BDA, which means we're actually double counting. Let me explain. Let's have two bubbles now. We have A, B, D, A. We can also form a second BDA. And then we'll have remaining a B and a C. Wait, let me count this. One, yep, one, two. No, there's no A here, just two BDAs, a B, and a C, and a D. Yeah. I have five bubbles, 5 factorial. These two bubbles are identical, 2 factorial, right? 5 factorial divided by 2 factorial gives me 60. Okay. And then my correct answer is going to be 1260 minus 60, which is 1200. Now, let me explain why we have to do this method. So what is this working out here missing? So on to the side, right? What's missing is that also over here. BDA, okay. Wait, I can copy and paste actually. Copy and paste. Okay. So if I have A and then BDA and then B and then D, no, BDA, B, bubble D, bubble A, bubble, and then B and then C, right? Consider this arrangement over here, and then consider the next arrangement of B, D, A, then BDA together as a bubble, and then B and then C. Okay? Functionally, using my like, I don't know, conscious thought, BDA, BDA, BC is the same thing as BDA, BDA, BC, right? They're identical. But with this bubble strategy, this bubble is different to this bubble, right? These bubbles are arranged completely differently. So even though functionally it's the same thing, realistically, I'm like double counting um these two BDAs over here. Even though it looks the same, the bubbles are arranged differently, right? So I'm double counting by a factor of two. So no, by a factor of two, sorry, no, I'm double counting by an extra 60 arrangements, right? An extra 60 arrangements of BDAs. So in that case, it would be 1260 minus 60, giving me 1200, right? Hopefully that makes sense. If it doesn't really make that much sense, put in the chat. I'll try to explain it in more depth. So yeah. But that's it for this question. A pretty hard one. So if you guys get this, then good on you. The next one is arrangements involving groups. So what's the first question? Barbara and John and six other people go through a doorway one at a time. In how many ways can the eight people go through the doorway if John goes through the doorway after Barbara with no one in between? So Barbara and John and six other people. So I'm gonna have Barbara and John together, so B and then J. And then I'll have six other people. So one, two, three, four, five, six. In total, I'm gonna have seven bubbles. So I'll have seven factorial ways to arrange all these bubbles, being 5,040. Now, Nikhil might ask, oh, but can't you arrange J and B like that, right? Isn't there going to be 7 factorial times 2 being 10,080? And what I'll say is that in this case, John has to go after Barbara, right? So he cannot like change his position. Therefore, we don't times by an extra 2, and this is my answer. For question 2 here, in how many ways can all the letters of the word parallel be placed in a line with the three L's together? So I have P, then A, R, A. My three L's are together. That's one bubble. And then E. So 1, 2, 3, 4, 5, 6. 6 factorial, right? But then I have two identical bubbles, these two A's, divided by 2 factorial, right? And my answer here is 360. Now, these three L's, you might be like, okay, but like a range of three L's, right? However, LLL is equal to LLL. You can't arrange them, right? There's only one way to keep them together, right? So if you want to be more specific, you can do 6 factorial over 2 factorial times 3 factorial divided by 3 factorial because it's all being repeated. So this is 1, which gives you 360 as well, right? So that's arrangements with groups. So now we'll do some more trickier questions, right? So the first question here is how many ways can 4 boys and 10 girls be arranged if Amy is exactly 2 seats away from Rachel? I'm gonna give you guys like 3 minutes to think about it and see if you get an answer. If you get an answer, put it in chat. But it is a bit like of a step up from the other questions we've just done. So yeah, if you don't get it, it's all good. It's a bit harder. Okay, do we have any thoughts on this question or like a possible method? Put in the chat if you do. Okay, Nikhil's given a crazy formula. Let me check this out. Times 2 over 4 factorial times 8 factorial times 8. Wait, 10 factorial times 8 factorial times 2 on 4 factorial times 8. Nikhil, I think you're missing some solutions or I misclicked like because you need some brackets there. There's a lot of division and multiplying going on. Um, okay, so I think Jackie has come up with he's nearly got the right solution. Um, so first of all, the first thing he tells me is we need to set up a group, right? So Amy is exactly 2 seats away from Rachel. So we'll start with like Amy being 2 seats away from Rachel. So there's one person in between. This is my first group. I have 4 boys and 10 girls. So in total, I have 14 people. And because 3 people are in this group, I have 11 other bubbles, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I have 11 bubbles, right? Now, from these 14 people, I have Amy, Rachel, and 12 others. So in this spot over here, as Jackie tells me, there is 12 people in the middle seat. Nikhil asks, is that not 1 seat away? So I think 1 seat away is like next to, and 2 seats away would be with one in between. That's the way I interpret it. Check with your teacher, but I'm pretty sure that's how you should do it. Because it's like first seat, second seat, third seat, and then it's like two in between. I don't know. But I'm pretty sure this is how you should interpret it. But yeah, again, check with your teacher. So yeah, so within this group, right, in the middle seat, I can put in 12 people, right? 12 can go in there. So just keep that in mind. Now, I'm going to arrange all 12 of these bubbles. So my first number to consider is 12 factorial, right? Arranging all 12 of these bubbles. And then the last number to consider is the fact that Rachel could be behind Amy, right? You can have another group where R and then someone in between and then A, right? Rachel is behind Amy. So therefore, I'm going to times by 2. So my final answer is just 12 times 12 factorial times 2, right? So 12 comes from putting like one of 12 people in between Amy and Rachel. 12 factorial is to arrange all 12 of my bubbles. And then 2 accounts for how Rachel can be either behind or in front of Amy, right? That's my answer, 24 times 12 factorial. The next question, in how many ways can all the letters of the word parallel be placed in a line such that R is in front of P? This question seems daunting, but there is a very quick trick you can use to find the answer. I'm going to give you guys about 2 minutes. So at 7:57, I'll come back, reconvene, and I'll see if anyone has got the answer yet, because there is a very quick trick for question 2. So yeah, give you guys 2 minutes for that. Oh, okay. James has gotten it. Yeah. James, that is correct. Um, that is a quick trick. Nikhil's got it as well. 1680. That's right. Jake's got it as well. Beautiful, beautiful. This is great. Good job, guys. So we have 8 letters. Um, so parallel. And then I appreciate how Jake just wrote the full formula. So it's a factorial divided by 3 factorial times 2 factorial because of the repeats over here. You have 2 A's and 3 R's. Sorry, not 3 R's, 3 L's. So it's 3 factorial times 2 factorial. And then this gives you all arrangements, right? All arrangements. And as James said, you have to halve it because logically, either R is in front of P or it's behind P, right? There's 2 cases. So for it to be in front of P, just times by half. The answer is 1680. And that's it. Okay, good job, guys. Next one we're going to do is arrangements with separation. So this is the gap method. So the logic here is that um, if you have unrestricted objects, right, you want to arrange them first, and then you place the restricted objects into the gaps in between them. So what does that mean? Like in this first example here, find the number of 7-letter words which can be formed from the letters of the word display if no 2 vowels are to be together. So we have 2 vowels here, only 2 vowels, I and A. Okay, so let's consider the letters D, S, P, L, and Y. Right, D, S, P, L, and Y. Let's put a gap in between each of these letters. Okay, because if you have a gap in between, this ensures that no 2 vowels can be next to each other, right? To arrange 5 objects, it will just be 5 factorial. Okay, but now we have to put in the vowels. So my vowel I has a total of 1, 2, 3, 4, 5, 6 options. There's times 6. And then my vowel A has a total option of 5. Because vowel I has taken up one of these gaps, A only has 5 more options. So my answer is 5 factorial times 6 times 5, giving me 3600. And if you're a bit more confident with the Perms and Commons formula, I would do 5 factorial times 6 choose 2. From these 6 gaps, I'm going to choose 2 of them. 6 choose 2 times 2 factorial. Okay. Yeah, 6 choose 2 is the same thing as 6C2 or 6 factorial over 6 minus 2 factorial times 2 factorial, by the way, which also gives me 3600, right? Identical. In how many ways can 5 boys and 4 girls be arranged in a row so that no 2 girls are together? I'm gonna do it quickly. So we have 5 boys, B1, B2, B3, B4, B5. In between, we have 6 gaps. Using my previous logic, it'll be 5 factorial to arrange all the boys. And then I'm gonna pick 4 gaps for my girls. So times 6, choose 4. And then I'm gonna arrange all 4 of these girls, just times 4 factorial, and the answer is 4,300, no, 4,000, 43,200, and that's it. Okay, sweet. Um, Nikhil asked, like, arrange the vowels together. Beautiful. I'm gonna go to like Nikhil's method as well for question 1, because he's doing a complementary method, and I'm gonna show you how that works. So he tells me um, let's arrange the vowels together and then minus the total of them not being together. So you might have seen like in probability, the probability of having at least, like 1 6 is equal to 1 minus the probability of no sixes at all, right? And that's the same logic here. So the total number of 2 vowels not together is equal to the total minus the number of vowels being together, right? That's the complement. So in total, I have 7 yeah, I have 7 letters in this word. Do I have any repeats? No. So my total is 7 factorial. And then I'm gonna subtract the vowels being together. And in that case, I would use the group approach, right? So I have I and A together, D, S, P, L, and Y. 1, 2, 3, 4, 5, 6. So this is going to be 6 factorial because I'm arranging 6 bubbles. But then I have to arrange I and A themselves because I can have IA or AI. So I'm going to times by 2. This gives me 5040 minus 1440, which is 3600. So yeah, good catch, right? There are multiple ways to do the same question. So just keep that in mind, right? The way I do it might not be the way you intuitively understand it, and that's all right. So that leads us nicely to like the next section, which is arrangements using complementary events, right? And for this question, in how many ways can 8 people be arranged in a row if at least one of 3 friends, Alice, Bob, and Charlie, must be separated from the other 2? This question is the exact same method as what Nikhil proposed, right? So 8 people being arranged. See, number of ways where at least one of A, B, C is separated is equal to the number of total arrangements minus number when they're all together, A, B, C together. Okay, that's equal to, I have 8 people in a row. That's 8 factorial. I'm gonna subtract. So A, B, C together, I'll have A, B, C as one bubble, and then I don't know, D, E, F, and G. This gives me 5 bubbles, so 5 factorial ways to arrange them, minus 5 factorial, times I can arrange A, B, C together. That would be 3 factorial. This gives me um, A factorial minus 5 factorial times 3 factorial, which is 39,600. Is that right? Let me confirm. Yep, that's the answer. Oh, wait. 1, 2, 3. Can I not count? A, B, C, D, E, F. 1, 2, 3, 4, 5. Oh, wait, no. I have 8 people. It's a H. Okay. 6 factorial times 3 factorial because there's 6 bubbles to arrange. This gives me 36,000. Okay, that's my answer using the kills method. This next part is about arrangements in a circle. So the intuition here is that in a circle, there's no fixed starting point. So if you arrange stuff in a circle, you are not accounting for rotational symmetry. For example, if I have A, B, C, and D, right, in a circle, that's the same as having D, A, B, and C. Because if I like, you know, highlight this and sort of twist it around, right, it's the same thing because it's a circle, right? Identical. So the way you treat this is that to do arrangements in a circle, right, instead of this being 4 factorial, right, my answer here to arrange these people on a round table would be 4 minus 1 factorial, which is 3. How do you do that? Well, let's say I'm gonna lock in person A into a spot here. So A has to be on the top, right? Once A is locked in, he's my point of reference. So relative to A, I'm gonna arrange D, B, and C. That's just 3 factorial, right? Um, and it doesn't really matter who's locked in because I can just like sort of rotate this and B is on the top, right? The entire point here is that I'm always going to choose one particular object, one particular person to be my point of reference, which is why if you're arranging n objects around a circle, the number of possible arrangements is n minus 1 factorial because one of these objects is our reference point and we're going to arrange the other n minus 1 objects, right? That's it. That's the formula. So, ooh, okay. How many ways are there for at least three odd numbers to be together when arranging 1, 2, 3, and 4 in a circle? This is a pretty hard question. I'm gonna put this on the other tab so I can have more space to work with it. And it didn't work. Crazy. I'll do it here anyway. Never mind. So how many ways are there to arrange this? So for at least three odd numbers, right? Either I have three odd numbers together and one odd number like separated, or I have all four odd numbers together, right? Because from 1, 2, 3, 4, 5, 6, 7, 8, I have four odd numbers and four even numbers. So let's treat the first case. I think four odd numbers together is pretty easy. So my first case is four odd numbers are together. Okay. So the strategy here is that I'm going to sort of arrange the even numbers with some gaps in between and then put my odd numbers into one of the gaps. So I'm going to have, 2, 4, 6, 8. There'll be a gap in between, right? So first of all, to arrange four even numbers around a circle would be 4 minus 1 factorial. Okay? That's simple. My second step is I'm going to pick one of these gaps from a four odd numbers. That's just going to be 4 choose 1, right? Which is just 4. The third option here is that so I have four odd numbers, right, in total. And then I'm gonna put them into a gap, and then I'm gonna arrange these odd numbers within the gap. So there's only one way to choose four odd numbers from a total of four odd numbers, and then I'm gonna arrange them to give me 4 factorial. So over here, I would have 3 factorial times 4 factorial ways to arrange the numbers in this fashion. Give me 576. 4 choose 4 times factorial times 3 times 4 factorial. Yep, Nikhil, that's correct. Yeah, good. And then the next one is three odd numbers, 3 odd together, and 1 not together. So same strategy. 2, 4, 6, 8. Right. I have 4 minus 1 factorial ways to arrange these even numbers. And then what I'm going to do is pick one of my gaps to be for the 3 odd numbers, right? So 4 choose 1. I'm picking one of the gaps for my 3 odd numbers. Then I'm going to pick 3 odd numbers out of 4 to be within this gap, right? So it'd be 4 choose 3, right? So this first one is going to be pick a gap for 3. So, yep. And then pick 3 odd numbers from 4. And then finally, right, once I've picked a gap for my 3 odd numbers, I only have 3 other options for my remaining one. So my next number here is 3. Right? This is going to be 3 possible gaps for my last odd number. And thus my answer here would be 3 factorial times 4 times 4 choose 3 times 3, which gives me under the maths times 4 times 4 times 3. Am I missing one? I am missing one. What I am missing here is that now I have to arrange all 3 odd numbers, right? So it would be 3 factorial, right? Arranging the odd numbers. Arranging odd. Arranging 3 odd numbers. So this should give me the correct answer now. Yeah, it's 1728. Because I have these two like separate cases, by the addition rule, I add them up. So 576 plus 1728 gives me 2304. And that's my answer. Okay, cool. Okay, next question. How many ways are there to arrange three teachers and five students in a circle such that no more than two students are next to each other? I'll give you guys like 2, 3 minutes to think about it. Put the answer in chat if you get it. So yeah, this question came up in a past HSC question. I think it was 2021. It was pretty tricky. So if you guys get it, then you're pretty much good for like year 12, right? So yeah. Okay, it's been like 3 minutes. Do we have a solution yet? So Jackie told me, so this is hella hard. Yeah, it is a difficult question. Um, which is why I put it in here, right? This entire lecture has a has like all the questions you need for like purpose of comms, right? So it is designed to be hard. 1440 to factorial. You're close, but you're double counting somewhere. That's the carry. Okay, I'm gonna go through this now. So first step, let's just draw it out. Um, so no more than two students are next to each other. This is our restricted group. So what we're gonna do is arrange our teachers. We have teach one, two, and three. Um, there are 3 - 1 factorial ways to arrange three teachers. Right, that's two. Okay. And then, so no more than two students are next to each other, right? What that tells me is that if I have one student in between teach one and teach two, then the other two have to be like this. So, i.e., in two spots, there should be two gaps between the teachers, and then the remaining spot should only have space for one student. Because if I happen to have one gap with three students, then, you know, either I have this situation where I have more than three, sorry, more than two, and like that's not something you can do, right? So at most, you can have two spots with two gaps for the students and then one remaining spot with the final student, right? So that's what's going on here. Now, the next step is we sort of got to choose the two gaps that have enough space for two students. So I'm gonna do three, choose two. There are three gaps, but I'm gonna choose two of them to hold two students, right? Three, choose two. My next step is going to be picking the students to actually go into these two gaps. Sorry, yeah, these two gaps. This will be five, choose four, right? Pick four students for like two people gap. And this is pick gaps with space for two. Okay. And then if I pick four students, right, one, two, three, and four, then my fifth student automatically has to go in this remaining gap, right? So keep that in mind. And for the final line of working out, I have to arrange all of my boys. So it would be 1, 2, 3, 4 factorial, right? I don't arrange this guy because there's no need to arrange him, right? But I can arrange in between these people over here. So for factorial, arranging for students in part 3. And my answer should be 2 times 3 times 5 choose 4, which is just 5, times 4 factorial, which is factorial times 5 times 3 times 2, 1720, right? Yeah. Um, Hopefully that makes sense. I think Kerry, you got 1440, but maybe you double counted somewhere. So yeah. Okay. The next one, this is a very small point, but it's in the syllabus, so I'm gonna cover it anyway. And it's to do with like circular wires slash bracelet slash necklace. So if you have to like arrange beads on a necklace, right? If you have like one, two, three, four non-identical beads on a necklace, the answer is 4 minus 1 factorial, right? Because it's a circle, divided by 2. Because there is like, I think flipping symmetry. Because if you have like A, B, C, D, and then you have D, C, B, A, these are the same necklaces, right? Because you can flip them across. It's a bit dumb, and so the quick way to get rid of all these flips is by dividing by 2. So in this question over here, in how many ways can 7 distinct beads be arranged on a circular necklace? It would just be 7 minus 1 factorial divided by 2, which is uh 360, right? The formula is if you arrange n beads on a circular wire, bracelet, or necklace, it is n minus 1 factorial divided by 2, right? Remember, it has to be one of these three words, or else you wouldn't use that formula. Um, Combinations, yeah, we covered that. So in how many ways can a committee of 3 men and 4 women be selected from a group of 8 men and 10 women? So quickly, the answer would be from 8 men, I choose 3, 8 choose 3, times from 10 women, I choose 4, it'd be 10 choose 4. Done. Part 2. A team of 11 students is to be formed from a group of 18 students. Among the 18 students are 3 students who are left-handed. What is the number of possible teams containing at least one student who is left-handed? So in total, right, total would be 18 choose 11, and we have left-handed. So number of possible teams where at least one student is left-handed, at least one is left-handed, is equal to the total amount of teams minus the number where no one is left-handed. No one is left-handed. Using the complementary counting stuff. So the total amount of teams is we have 18 students, we're choosing 11, it's 18 choose 11. Subtract, no one is left-handed, so that would be we're only picking 11 students from 15. Why 15? because three students are left-handed, right? So we're only picking students from the right-handed group, which is 18 minus 3. And this gives me a value of, choose 11, 30,459. That's my answer. Now, this is an interesting case, right? Selection of groups of identical sizes. And so for this one, like keep your ears open because you could lose an easy mark to a question like this. So let's say, for example, right, I have four people. I'm picking two teams of two, right? So I can have four choose two for picking my first team times two choose two for picking my second team, right? And then my answer would just be 4 choose 2 times 2 choose 2 is just 6. The answer is wrong. But, I'm picking 2 for the first team, picking 2 for the second team. Why is my answer wrong? Well, it comes down to a very like small detail, which is consider A, B, C, D. I have A, B on my first team and C, D on my second team, right? But what if I have C, D on the first team and A, B on the second team, right? Remember, these two teams are indistinguishable, right? And what's important to note is that it doesn't matter like if they're in a like, a team on the left side or the right side. What's important is that AB is separated from CD. So even though I have AB on my first team, CD on my second team, and CD on my first team, and AB on the second team, these are the same case because AB is separated from CD. So my answer is going to be actually 4 choose 2 times 2 choose 2 divided by 2 factorial, which is 3. And that's correct. And it's 2 factorial because there are 2 factorial ways to arrange the team, right? In this practice question over here, in how many ways can 6 distinct items be divided into 3 groups of 2 items each? If I have 6 items, I would do okay, 6 choose 2, right? That's my first team, times 4 choose 2, that's my second team, times 2 choose 2, that's my third team. But I can arrange 3 teams in 3 factorial ways, right? If I have a first, second, and third team, I can also have a third, second, and first team, a first, third, second team, and so on, right? These teams are indistinguishable. They can be arranged. We divide by 3 factorial, which gives me an answer of 6 choose 2 times 4 choose 2 times 2 choose 2 divided by 6, 15. That's my answer. But then my next question, right? 6 students are to be divided into 3 labeled teams, red, blue, and green, each with 2 students. In how many ways can this be done? 3 labeled teams. Because it's 3 labeled teams, these are distinguishable teams. They're different, right? So I'm picking 6 choose 2 for like team red, times 4 choose 2 for team blue, times 2 choose 2 for team green, which gives me 90 possible teams. I don't divide by 3 factorial because a red, a blue, and a green is different from like a generic team, right? If I have A, B, C, D, and E, F, right? A, B could be the red team, C, D could be blue team, and E, F could be green team. And let's say I have C, D as my red team, A, B as my green team, and E, F as my, sorry, A, B as my blue team, and E, F as my green team. These two cases are different, even though AB is separated from CD, which is separated from EF. The thing is, we have different values attributed to them. AB is red in the first case, but AB is blue in the second case. These two cases are different, right? And that all comes down to knowing which teams are like indistinguishable or not, right? This one, they're labeled. The first one, they're unlabeled. Okay, now we've reached like the last section of Permutations and Commas, where we go through a bunch of like harder questions, right? So the first one is the stars and bars method. You should be aware of this one for sure. I'm gonna like put a massive asterisk here. So what is the number of ways to distribute 8 identical balls in 3 different boxes, none of them being empty? Or what if the boxes can be empty? So it's 2 questions within 1 question. I'll give you like 2 minutes to think about it. Put the answer in the chat if you've gotten it, because it can be done quite quickly. And if you're completely stuck, it's fine because no one really sees this sort of question until they see it in an exam, right? So I will cover this. So yeah. Ooh, okay. Yep, that's correct. So Jackie's got part A. Jackie, would you like to unmute and explain how you got the first part of the question? Or nah? You don't have to if you don't want to. Okay, you can type it. Yeah, sure, type it out. But while he types it out, I'll give you guys a clue. So like it's called stars and bars, right? We have 8 identical balls. So just like draw out 8 stars, right? One. Or just do like 8 circles. Stars are too hard. 4, 5, 6, 7, 8. Right. We have 8 circles. Um, and the idea of a bar is that we have a way to separate these balls. So you might know, like, if you want to cut a piece of wood into 3 pieces, you make 2 cuts, right? If you want to separate 8 balls into 3 different boxes, um, if you want to separate 8 balls into 3 different boxes, you need 2 bars to sort of separate them. Okay, so Jackie's put up his solution. We have 8 minus choose from and 3 minus 2. Okay, so for Jackie, there's two. So Jackie has given me a different solution to the one I was thinking about, right? So I'll do my method and Jackie's method. Okay, so to separate 8 balls into 3 boxes, we need 2 gaps. The first gap, well, let's draw the gaps first. We have 1, 2, 3, 4, 5, 6, 7. Right. We have 7 gaps in between. So what I can do now is from these 7 gaps, I'm gonna choose 2 gaps to be my dividers, right? To have my bar, right? So my answer is just 7 choose 2, right? Which is 21. I have 7 gaps. I pick 2 in order to separate my balls. Jackie's method is, he says, there are 5 plus 3 minus 1 balls to choose from. And 3 minus 1. Huh. If 5 plus 3 minus 1 balls to choose from. Okay. And 7 balls to use. 3 minus 1 balls to use. Balls to choose from. 5 plus 3. Yeah, wait, I'm a bit confused as well. Okay, I'm gonna skip Jackie's method for now. But also yeah, another way to think about it, right, is that given that at least um yeah, given that each box has at least one ball, right? So if we have 3 boxes, they each have one ball each, right? One ball, one ball. That means that we have to now arrange 5 identical balls, as well as 2 dividers. So what does that mean? I have 5 balls, 1, 2, 3, 4, 5, and I also have 2 dividers. So to arrange all of this, it would be 7 factorial divided by 5 repeats for the balls times 2 factorial, which gives me 21. I sort of prefer this first method because it's a bit more intuitive. You're picking 2 gaps, but this one also works because if you arrange, you have this case where so in this case here, you have 5 balls going into box 1, 0 in box 2, 0 in box 3. You also have the following arrangement, like 0, 1, 1, 2, 3, 4, a divider, and nothing. So this would be 1 in box 1 and 4 more in box 2, right? That works as well. I think the second method, however, it works better for the second part of this question because the second part is, what if the boxes can be empty, right? So what you can do for this is that you can have 1, 2, I'll erase some of this part. Let's delete all of that. 1, 2, 3, 4, 5, 6, 7, 8. We can have 2 dividers. And then what I can do now is arrange 10 of these objects, so 10 factorial, divided by my 8 repeats for the balls, times 2 factorial, where I have 2 repeating bars, which gives me 45, right? So that's the stars and bars method, and that's what you'll use when you're like separating objects into various boxes, if that makes sense. Um, okay, part 2. Ooh, you know what? I'm gonna do question 3. So question 3 is, from 9 men and 6 women, we're gonna select a 6-person committee with at least 4 women. 2 particular men refuse to serve together. How many possible committees? So how many committees are possible if order does not matter? Um, so how do we approach this? I'm seeing here in the question, there's at least 4 women. In a total, I have 6 women. So probably the best way to deal with this question is in cases, right? So I can have, case 1 is, we have 4 women. Case 2 is 5 women. Case 3 is 6 women. So case 1 is 4 women and 2 men. I have 6 women. I want to pick 4. 6 choose 4. And then I have 9 men. And because I have 4 women and I need a 6-person committee, I need to choose 2 men. Times 9 choose 2. I have a minus sign here. And the reason for that is that if I'm picking 2 men, there is a chance I pick 2 men who refuse to be like together. So in this case, I'm gonna subtract 6 choose 4, me picking all the women, times the case where I pick to two forbidden men. Two choose two. From two forbidden men, I pick exactly two. That's done in one possible way. That is 540 minus 15, giving me 525. Next case, five women, one man. So that would be six, choose five women from six, times nine, choose one. Pick one man from nine. Note that in this case, I don't have to subtract any like forbidden cases because if I'm picking one man, there's no way I can pick two men who refuse to serve together. So that's like out of the question. And then thirdly, six women. That's straightforward. It's just six, choose six. There's only one way to pick six from six, right? So my answer is 525 plus 54 plus 1, giving me 580. And that's my solution. Question 4, question 5. Okay. Question 4 and 5 are like, I reckon like stuff you could get in your exams. So I'm going to go through them for sure. So question 4. The following eight tiles are taken from a Scrabble set. A, B, B, C, D, E, F. How many different four-letter permutations can be formed from these eight tiles? So the only way to do this, I reckon, is by doing it in terms of cases, because not only are we picking four letters from a total of eight, but then there are like repeats being involved. You know, you have two A's, two B's, you know, that makes stuff a lot more confusing. So I'm gonna think about three cases here. The first case here is I have no repeated letters. That makes my life a lot easier. No repeated letters, right? So I'm gonna pick four from A, B, C, D, E, F. My next case is exactly one letter appears twice. Exactly one letter appears twice. Give me more space. Move it up here. And my third case is I have two different letters appear twice. Okay. So the first case, I have six options, A, B, C, D, F, and I'm picking four letters from that. As we know, using our permutations like formula, it's just 6p4, right? Or it's the same thing as 6 choose 4 times 4 factorial, which is just, I don't know what that is. What's that? 360? It's 360. Next one is exactly one letter appears twice. Let's say we have two A's being used. Case A is two A's, okay? So if I have two A's being used, therefore I only have two more letters to choose. From B, C, D, E, and F, I'm going to pick two letters, right? That's 5 choose 2. That's 10. So now I have A, and then letter 1, letter 2. Okay? And there's 10 ways to pick letter 1, letter 2. Now, how do we arrange AA, L1, L2? That would just be 4 factorial divided by 2 factorial because my A's are repeated. So, and finally, my answer for 2A's permutations would just be 10 times 4 factorial over 2 factorial, which is equal to 120. But what if I use 2B's? If I use 2B's, then the same logic still applies, except instead of having B, C, D, E, F, I would have A, C, D, E, F, but the same numbers in total. So if I have 2B's, then I would have 120 permutations as well. And then finally, two different letters appear twice, okay? I have A, and B, B. No need to like select anything, right? I already have my four letters, right? I'm chilling. This would just be 4 factorial divided by 2 factorial times 2 factorial because of my repeats, which is 6. So in total, I have 360 plus 120 plus 120 plus 6, giving me 606. And that's my answer. So again, you might be lazy and I think like, oh yeah, like this might be a quick trick. Sometimes there isn't a trick. If you get stuck, use casework to approach the question. And finally, we have a question about cards, right? selecting cards from a pack of 52. And Aiden, you might want to like look at this one because you gave me a question about having a triple and a double. And I think this one sort of relates to it tangentially. So yeah. So 5 cards are selected from a standard pack of 52. Find the probability of having exactly one pair. 5 cards. I'll draw 5 like gaps or like 5 dashes. Exactly one pair. So I'm gonna have, this is my pair, P1, P2. Then I'm gonna have 3 other cards, card 1, card 2, and card 3. The thing with a pair of cards is that you have the same rank. So ace, 2, 3, 4, 5, 6, 7, jacks, queens, kings, right? That's your rank. But you have different suits. Okay. So what I can do is, let's say I'm gonna 13 choose one where I pick the rank of my pair, pick the rank of the pair, times 4 choose 2, because I'm picking 2 suits, right? Note that a pair cannot have 2 cards of the same suit because you can't have two like diamond aces, can you, right? One has to be diamond, the other one could be clubs or jacks. Well, no, clubs, no. Clubs or what was the other one? I kind of forgot the names. So you have diamonds, hearts, clubs, and spades. Yeah, right. So if you have a diamond ace, right, the other ace must be a clubs, spades, or hearts. So I'm gonna do 4 choose 2 to pick the suit, right? Pick the suit of P1 and P2. Then I have 3 other cards, right? So because I want exactly one pair, that means that one of my ranks is out of the question, right? If I pick an ace for my first pair, I cannot have an ace in any of these 3 cards. So I'm gonna do 12, choose 3. Okay. Note that I'm doing 12, choose 3 instead of 12 times 12 times 12, right? Because I must have exactly one pair. If I give the option of 12 ranks to each of my 3 cards, there is a chance I might have a second pair or I might have a triple. Yeah, I could have a triple, right? So in that case, I'm doing 12, choose 3, such that I have like no, um, I guess, repeats, right? So it would be a way to pick 3 distinct ranks. But, and if I pick 3 distinct ranks, right, what that means for my suits is that each of these cards can be one of 4 suits. Be 4 times 4 times 4, right? Because the ranks are already distinct, it doesn't matter if the suits are like the same as well, because if the suits are the same, but like your rank is distinct, it can't be a pair. So it's times 4 times 4 times 4. And note that I don't have to arrange this. I won't do like times 5 factorial or whatever for the fact that I'm selecting, I'm not arranging. So it's choice. This is how many total exactly one pair combinations I have. But because the question is probability, I need to figure out the total cases in which I have one pair. That's just 52 choose 5, right? Picking 5 cards from 52. So my answer is 13 choose 1 times 4 choose 2 times 12 choose 3 times 4 cubed over, um, what's this going to be? 52 choose 5, giving me about 0.4226. And that's the answer. Okay. So for everyone here, it's getting quite late. So what I'm gonna do is upload like my lecture notes with complete solutions onto the Zoom chat. However, I'm still gonna be here answering question 2, as well as 3 or 4 more questions that were put into the chat. So if you want to stay for those questions as well, feel free to. Those questions are pretty hard, and I do want you guys to like be able to solve those. But I'm going to put in the notes in the chat so you can download them on your end. Um, so the solutions are all being uploaded. And is it being uploaded? Give me a second. Yeah, it's been uploaded, but I'm still going to go through with some other questions to make sure you guys are on top of things. Okay. So question 2, from 8 men and 7 women, we form a 5-person audit committee, a president, vice president, dictator, military, and secretary. 2 men refuse to serve together, and 3 women refuse to serve together. How many audit committees are possible? In question 3, we just selected, right? It didn't matter what the order was. It didn't matter what like role was given to them because there is no role given to them, right? But over here, we have distinct roles, which means we do have to be careful about how we arrange things. So let's start with this question. Okay, so we have a president, vice president, uh, dictator, military, and secretary, right? So how do we approach this? 2 men refuse to serve together and 3 women refuse to serve together. How many audit committees are possible? To approach this, I'm going to use a Venn diagram. This Venn diagram represents all possible committees. Okay. In one circle, I'm gonna call this circle the forbidden women, and the other circle will be the forbidden men, right? And note that I did include an intersection here because there is a case where 2 men, well, 2 forbidden men and 3 forbidden men, sorry, 3 forbidden women could work together because 2 and 3 would form a 5-person audit committee. Why this is important is because it plays into how I'm going to set up you working out for this question, right? So it all comes down to this inclusion exclusion principle. So the valid committees, right? The total valid committees is equal to all possible committees, right? Minus forbidden men, or like I'll say FM, minus forbidden women, plus forbidden women and forbidden men, right? So previously we had like, for a team of no, of at least left-handers, it would be all the possible teams, subtract the teams where there's only right-handers, right? This is a bit more complicated because you have overlap, right? And the reason why I have to add forbidden women as well as forbidden men is because of the fact that the union of these two circles is equal to the forbidden women by themselves plus the forbidden men minus the forbidden men and forbidden women. Because if I visually represent this, right? If this is blue, this is red, this is green, right? If I subtract a forbidden men, I'm subtracting a blue as well as a red, and then forbidden women, sorry, no, men, a green and a red. For the forbidden women, I'm subtracting a blue as well as a red, but I've subtracted like too many reds, right? Like I only have one red section. So I need to add back a red section, right? That's what's going on, if that makes sense, right? So let's figure out each of these individual cases. So all possible committees, right? All possible committees. It's just I have 15 people going for 5 spots and it's ordered 15P5, which is a really big number, I think. 360,360. The second one is committees with forbidden men in them, right? So for this one, I'm gonna pick 2 forbidden men from 2 forbidden men. Then from the remaining 13 people, because remember, I have 15 people, I've picked 2 forbidden men, I have 13 remaining. From them, I'm gonna pick three other people to make my total 5 spots. And then I have to arrange everyone times 5 factorial, giving me 34,320. For the forbidden women, it would be, so from 3 women, I'm choosing 3. Which is just, yeah. And then I have 12 other people left. I'll pick 2 people from there. And then I'm going to arrange them. So it's times 5 factorial. 15. Oh, sorry. Yeah, you're correct. Um, as Jimothy says, it's 15p5 mind blank. Yeah, he's correct. Yeah. But it's still the same number. So back to forbidden women. So it'd be 3 choose 3 times 12 choose 2. So being 2 of everyone else. Times 5 factorial to arrange. 77,920. And the case where you have forbidden men and forbidden women, it would be so I'm gonna pick 2 forbidden men from 2 forbidden men, pick 3 forbidden women from 3 forbidden women, and then arrange, giving me 5 factorial. So my answer is going to be 15p5 minus 34,320 minus 7,920 plus 5 factorial. And that's my answer. And yeah, so that's these lecture questions completed. And now I'm going to go through some of the questions I'll put up in chat. So I'll start with Aiden's question. And Aiden, you might want to like unmute or like ask me any questions because you asked me this. So like maybe you have things you're unfamiliar with. So his question was, I'll write it down. The 6 faces of a number of identical cubes are painted in 6 distinct colors. How many different cubes can be formed? So this is a bit challenging, right? Because you have a cube. I'm so bad at drawing. It has 6 faces, right? So you have 6 different colors with 6 faces. You might say, okay, my answer is 6 factorial, giving me 720, right? The issue is a circle can be rotated, a cube can be flipped, right? And as a result, you have so many different like rotational symmetries with the cube. So how do we deal with this? Um, First of all, oh, well, let me make sure I'm like, yeah. First of all, what we're gonna do is let's consider, um, like imagine this like tissue box here is my cube, right? I'm gonna set this like I'm gonna set the top face to be locked in, right? It's locked in. And now when I like arrange this cube, right, I can rotate this cube 0 degrees, 90 degrees, 180 degrees, or 270 degrees, right? So there are 4 possible ways for me to rotate this cube around. So there are 4 rotational symmetries. And then when I say I'm gonna lock in a face, right? This top face can be one of 6 colors. So there are 6 ways to like to lock in top face. And then there are 4 ways to rotate the cube. So I'm gonna overcount by a factor of 24. So my final answer would be 720 divided by 24, giving me 30. Does that make sense? It's a bit like iffy, this method. Well, like it is the correct method, but like it's a bit hard to understand.
Can you explain like the bit where you have to rotate the cube?
Yeah. So let me draw the cube out. Okay, we have 6 colors, right? Let this be color 1, 2, 3, and 4, right? On these spaces over here. Okay. Now imagine like in this static position, let me copy and paste. Copy and paste. Let's say I move all of these colors across by 1. So be 1, 2, 3, and 4. You see how even though, like looking at it, it's different, but it's not because I just rotated it, right? So if I just did 6 factorial for my total options, these 2 cubes are counted as distinct. But in fact, when I rotate cube 1 around to give me, okay, I can't really do it that effect there. But if I rotate cube 1 to cube 2, they're like completely identical. And then if I rotate it one more time, so here I have 4, 1, 2, 3. If I sort of move this to the left, it ends up looking like the other 2 cubes, right? And then again, if I do it one more time, 3, 4, 1, and 2. This cube you might think is distinct, but if you rotate it, you come back to cube 1, right? So there are 4 ways to rotate it, which means that we're overcounting by 4. And then because there are 6 ways to set the top face, eventually we're overcounting by 24, which is 6 times 4. 6 for the top color and 4 for the rotational symmetry. Does that make sense?
Wait, so if you picked like one color for the top cube and then you sorted out the rest, and if you picked a different color, you actually get the same thing. So you just overcounted 6 times.
Yeah.
All right.
Does that make sense?
Yeah, yeah, I get
Yeah.
it.
Because it's a bit,
Thanks.
um, I did this question like as well in year 11. Like I was stuck on it. But that's like the way you should understand it. And then, so your next question is a die fits perfectly into a cubical box. How many ways are there of putting the die into the box? Of putting the die into the box. Given you understand question A, hopefully, what's the answer for question B?
24.
Why?
Because you can choose a color in 6 ways,
Yeah,
and then you can like choose the turning bit in 4 ways.
4 ways, right? But instead of a color, we have like maybe you have the 5 dots, right? So if you arrange it in 4 ways, it looks different each way. So that's sort of what's going on there. So you have 6 different numbers you put on top, and there's 4 ways to orient the cube. Therefore, the answer is just 6 times 4. The answer is 24. Right? So that's why part B is connected to part A. So yeah. Cool. Let's look at your other questions. There were a couple you had. Okay. Huh. For this question. Okay. Your question is this is a funny solution. Consider the digits 9, 8, 7, 6, 5, 4, 3, 2, 1, and 0. Find how many 5-digit numbers are possible if the digits, this is really messy handwriting, sorry. are in part one, ascending order, part two, descending order, and part three is why does this involve unordered selection? Okay, so oh yeah, and zero, yeah. In total, we have 10 digits, right? 0 to 9, which is this 10. Now from 10, where we have 5-digit numbers, so would have 10, choose 5. Okay. Aiden, what was your next step? Once you got to 10, choose 5.
What was your question?
What was your next step? So I'm assuming you did 10, choose
Yeah,
5.
I just got confused. Like,
Yeah, yeah.
um, if I pick like five numbers, say I pick like 9, 3, 7, 2, 1,
Yeah.
like that set can be organized in different ways. But
Okay.
if I use 10C5, I'm just picking it and then organizing it later. So
Yeah.
I don't know how that makes sense.
Okay. So 10, choose 5, is just we pick the numbers straight up, right? We pick any 5 digits. And then you might have seen in my previous working out in my lecture, I would often pick like, 3 odd numbers from 4 and then arrange the odd numbers times 3 factorial. So 4 choose 3 is me picking, and then 3 factorial is how many arrangements are there? Okay. So it's you pick times the arrangements. I have 10 choose 5 ways to pick. How many ways are there to arrange 5 numbers in ascending order?
Ascending?
How many ways are there to arrange 5 numbers in ascending order?
One way.
One way. It's
Yeah.
5 times 1. That's your answer for part I, which is 252. Similarly for descending order, right? Um, there's only one way to like arrange it going downwards. So it's just 10 choose 5 times total arrangements, just one. So 252. So
But can you start with zero?
can you start with zero? What do you mean by start with zero? Oh, it's like
Because it's a number.
yeah, like if you start with zero, I mean that wouldn't count as an arrangement, would it, right? So
So your
like
number could be 0, 3, 5, 6, 7.
0, 3, 5, 6, 7. Yeah, it's
That
more.
doesn't count, does it?
It's like a series. I don't know. I reckon it counts. Like,
Well, I'll check the answers.
I have the book in front of me. Let me check this for you. Um, 14, 14. Because
Excuse me, sir.
yeah. Who was that?
It's Jimothy here.
Oh yeah, sweet. What's your
I'm
question?
just wondering, would that count, or would we have to do 9 choose 5 instead because there's a zero?
Wait, isn't it 9, choose 4?
Oh, actually, wait, Aiden. What does the answer say? I think you'll be right. It's 94.
But the answer says 126.
Well, ascending or descending?
Yes, 94.
94. Okay. The digits are in ascending order. Okay. No, I think you are right with that. Yeah. It's not a sequence. How many fives is possible if the digits are in ascending order? Yeah, so we can't pick 0 to be the first one. Yeah, so okay. Same logic, but it's 9 choose 4 because from 0 to 9, if you have 0 as your first number, you can't have a number that starts with 0, right? So you from 9, no, not wait, is it 95?
So
9.
I think it's 9C5.
Yeah, it's 95, not 94. And that gives you 126. So yeah. And for
Oh, yeah,
this
my fault, my
order,
fault.
it should still be 252 because you can have your last digit being 0 as well. So that's just 10, choose 5. Yeah, that's a good call. See, like that's like a common trick to trick, right? Numbers can't start with 0. Yeah. Why does this involve unordered selection? Um, because like the numbers are either like ascending or descending. Like the order is fixed. It doesn't really change. So the only thing that varies is what digits do we select. So that's why it mainly involves unordered selection. Yeah. Okay, the next question. From a standard deck of 52 playing cards, how many 5 cards contain one pair and 3 of a kind? 3 of a kind, same rank. One pair and 3 of a kind. Beautiful. Okay. Aiden, walk me through this question because we did like a similar one for the last one, right? In the lecture. How would you do this one as well? What's your
Uh, so you have to like pick, just say like you pick a suite first.
okay? A suit. Okay, wait. Let me draw it out. So we have pair 1, pair 2, 3 of a kind. 1, 2.
Wait, does that mean like it's the same number?
What do you
Like
mean? Yeah,
seven of
same rank, same rank. Yeah, yeah.
oh,
Right. Let me write the question down. How many 5 card hands contain one pair and 3 of a kind? By the way, for everyone else, make sure you're like trying it out as well. So, yeah. Yes, so Aiden. So you're picking the suit, right? So what's my equation?
uh,
Oh no, sorry, you're picking the rank, right? I don't know.
wait, do I pick the rank for like?
I don't know, up to you. It doesn't matter.
If I choose rank, then 13C1,
13T1. Next.
and then choose the pair. Is it like 3C1, or is it no, or is it 4C2?
42.
Oh yeah, 4C2.
Yeah. Right.
Oh, shit. Yeah.
Next.
And then you can't choose from this. Wait, so it has to be from a different number now, yeah?
Yeah. Correct.
So 12. Uh, the 12C1,
Beautiful.
and then you choosing 11C2. What the hell?
11C2. Wait.
I might be tripping.
So you picked 12C1. That's your rank, right? What's remaining?
Oh, wait. No, like, um, I have to choose like the other. I have to choose three
From
from like the same like rank here.
same rank, but it's 3 of a kind. 3 of a kind, it just means they all have the same rank, right? So we've picked your rank for all 3 already. 12C1, right?
Yeah.
It's like half of the pairs. You picked 1 from 13 for both of them. We picked 1 from 12 for all 3. We picked the rank. What's remaining?
Oh, 4C3.
4C3, right? We're picking 3 suits from a total of 4. And
Oh, okay.
that's your answer. 3744. Um, does that make sense? Is that correct?
Well, let me check the answers.
All right.
Yeah,
Oh,
that's correct.
nice. Okay. Okay, the next question. This is a dumb question. Find the largest power of 7 that is a divisor of 100 factorial.
But that's not really an exam question, right?
Yeah.
Is that more Olympiad?
It's not like it's not really comes in comms, but I'll like tell you how to do it anyway. So if you have 100 factorial, right?
Yeah.
So that's what 100 times 99. Oh, this is a hard question. Oh. 100 times 99 times.
Oh, excuse me. What's the question?
Oh yeah, sorry. I'll write it out. Find the largest power of 7 that is a divisor of 100 factorial. Find the largest power of 13 that is a divisor of 100 factorial. Okay, so Aiden, in regards to as to whether this can be an exam question or not, I'm gonna say yes, because it's still a counting question. So I'll take back what I said. You might see it in an exam. And how do you do it? So first of all, let's find all the like numbers divisible by 7, right? So 100 divided by 7 is like 14.29. You kind of have
Wait, you just round down to 14?
you ran out of 14, right? Floor function, which is 14. Okay. So you have
Yeah.
14, but also you have another case of 14. So you have 7 squared, right? Which is 49.
Yeah.
Right. So 49 has 2 sevens. And then you have
Oh,
times
okay.
49, which is 98. That also has 2 sevens. So even though you have 14 numbers that are divisible by 7, you have an additional 2 more sevens because of 7 squared, right? Does that
Yeah.
make sense? So I think the answer will be 16 for this one.
Yeah, that's correct.
Okay. And for the largest power of 13 dividing 100 factorial. So 100 divided by 13 floor function is 7. You round down, right? And
Yeah.
because like 13 squared is 169, that's beyond the scope of 100 factorial. Not important. Answer is just 7. There's 13 to the power 7.
Oh, okay, yeah.
Yeah. Easy. Okay, I'm having a look for the more questions. I think that's it from you, right? So are you all straight with that?
Yeah.
Okay, sweet. Does anyone else have any other questions?
No, I'm good, sir. Thank you so much.
You good? Okay, I think Jackie's good. Hopefully Carrie and Gigi are good. Okay, so I think that's it for today's lecture. If you want to stay up to date to all of Summit's lectures, please follow our Instagram. We have like our schedules being posted there all the time. The next extension 1 masterclass will be on polynomials. So if you need help with that, check out Instagram for like dates and times. But otherwise, I'll let you guys go. And yeah, I hope to see all of you at that next lecture. So yeah, see you guys. Bye.
All right, thanks.
Thank you.